Today we are going to see formation of PN junction. To form a PN junction, we will take a semiconductor crystal, either silicon or germanium. Then one end we will dope with a trivalent impurity. Means this region up to this width, it will be doped with a trivalent impurity, so that this region will be P-type semiconductor, and the remaining portion will be doped with a pentavalent impurity, so that this will be N-type. And there is a junction. This is represented by junction. So across the junction, on the either side, left side, there are large number of holes because it is P-type semiconductor. Here it has large number of electrons because it is N-type semiconductor. So here holes are the majority carriers and the electrons are the minority carriers. Here electrons are the majority carriers and holes are the minority carriers. Okay. Here in addition to the holes, there will be negative ions. Negative ion means ions that means acceptor ions are there. Because here we have a hole, so along with the one hole, there will be an acceptor ion. For example, a boron ion will be there. So along with each hole, there will be an acceptor ion. Along with each electron, there will be a donor ion. Arsenic, for example, we can take arsenic, a donor ion. That is not shown here. After the basic process, we will show the ions, the acceptor and donor ions. Okay. Now this is the situation. We have formed a junction of P side and N side. And this is a junction. This is P-type semiconductor and this is N-type semiconductor. Now when the junction is formed, what happens is, there is a strong attraction between the electrons and the holes. Electrons have negative charge. They are equivalently having positive. There is strong attraction. This electron will come to this side. So they will move towards a junction. And what happens is, these electrons will be trapped in the hole. So hole is the vacancy. So the vacancy will be completed. When the vacancy is completed, what happens is, here electron comes here. Here electron comes to this side. Here also comes to this side. These three electrons and these three holes, they will be neutralized. Okay. When it is neutralized, what happens is, here we can draw. So I have told you that along with these electrons, there will be positive ions. Positive ions means they are donor ions. So we can draw the donor ions. Okay, these electrons and these three holes were neutralized. Now what is exposed in that region? In that region, ions will be exposed. Here positive ions are exposed. These are donor ions. And here negative ions are exposed. These are acceptor ions. Okay. In P-side semiconductor, we have holes and we have acceptor ions. In N-type semiconductor, we have electrons and donor ions. Now when the electrons and the holes were neutralized, these ions, immobile ions, they are immobile charge carriers, they will be exposed. Now, so here initially what happened? Electrons from the N side crossed the junction and holes also crossed the junction and they have neutralized. Electrons move in this direction. This will create some current. And this current is called diffusion current. So electrons will diffuse the junction and combine with the holes. This process continues further. These electrons can come and combine with these three holes. So the diffusion current starts to continue. Now I am drawing these three electrons will come to this side and these three holes also will be neutralized. Okay, the holes will disappear. Again, what I can draw three more positive ions exposed here. Means these are the donor ions and these are the acceptor ions. Okay. Now, here we can see an electric field. Initially, the diffusion current is very large because large number of electrons cross the junction. There is large diffusion current. Now, what happens is, we can see that here we have a strong positive electric field, positive charge, concentration of positive ions. Here, concentration of negative ions. It will create an electric field. From positive to negative, we can say in this direction there is an electric field created. This region do not contain any charge carriers. Okay, I will draw the electron These are the minority electrons. I will draw the minority electrons here. This region contain only here positive ions and here negative ions. This region do not contain charge carriers like holes or electrons. So this region is called the depletion region. This is a depletion region. The region depleted of any movable charge carriers. Okay. Now there is a potential difference. Strong potential difference. Here a strong positive charge, strong negative charge. This will create a potential difference. We can draw the potential difference like this. Here negative charge in low potential we can draw. Here positive charge. This is high potential. So high potential and low potential. Here exists a potential gradient. So this is called energy. There's an energy gap, or we can say there's a potential gradient. Or we can say this potential is called a barrier potential. So this region acts as a barrier, and there is a potential difference between this negative region and positive region. The potential difference is called a barrier potential. For silicon semiconductor, the barrier potential is about, we can say the VB is about 0.7 volt, and for germanium, this is for silicon. If you have germanium, this value is around VB is around 0.3 volt or 0.2 or 0.3 volt. This is called barrier potential. Now further, this electron will try to come here, but the problem is that these electrons are repelled by the strong negative potential here. Holes will try to reach here. The holes are repelled by the strong positive potential. That's why it is called a barrier potential. So there is a potential gradient existing between two sides of the junction. Here a strong positive negative potential, here positive potential, positive at high potential, negative at low potential. We can see there is a potential gradient exists from left side to right side. Here low potential and here high potential. So these electrons, even though they have energy, they are not able to overcome this potential difference, barrier potential. So they cannot come here. So the diffusion current, this is called diffusion current. Diffusion current means the electrons in n side, majority carriers in n side move towards p side, and majority carriers in p side holes move towards n side. So they diffuse, and the current is called a diffusion current. Now in addition to diffusion current, there is one more current. Here we can see minority carriers, two holes are there, two electrons are there. There's a strong positive potential, there's an electric field. In this electric field, they can move. Electrons can come to this side. Electrons can move from p side to n side. These holes can move from n side to p side. This is called drifting, and the current is called drift current. So we have two types of currents: drift current due to the minority carriers, and diffusion current due to the majority carriers. So they also can come. These two holes can come to this region because of attraction of strong negative potential. Strong positive potential can attract these electrons. This is called a drift current. So we have two types of currents. First one you have seen diffusion current. Initially it is very large in value. Diffusion current, but diffusion current is very large initially. Drift current is very less initially. But afterwards, after some time, whenever the process continues, the drift current increases. Drift current. So there are two types of currents: drift current and diffusion current. Diffusion current is due to the majority carriers, and drift current is due to the minority carriers. Now the situation is that the drift current is equal to the diffusion current after some time equilibrium. Now the net current is 0. Now no further flow of charges. This barrier is created. The barrier will prevent further diffusion or further drifting. Okay, this is called a barrier. The potential of the barrier is called a barrier potential. It is around 0.7 volt for silicon and 0.3 for germanium. And this junction is called a PN junction. So at the junction region, there are no charge carriers, only ions. Immobile ions are there, no movable charge carriers. That's why it is called a depletion region. So in this manner, a PN junction can be formed. And this PN junction is having many applications. We can connect external battery in two different ways, called forward biasing and reverse biasing. And it is having many practical applications also. That we will see in the next class. Okay, thank you.